You might describe this as a red liquid, and this as a clear liquid, and this as a blue light bulb, but there's more than meets the eye to each of these types of matter. With PASCO's UV-Vis spectrometer, you can investigate the invisible properties of solutions, chemical reactions, light, and atoms across a wide range of wavelengths. The UV-Vis spectrometer has a wavelength range from 180 nanometers to 1050 nanometers. This range includes a portion of the UV range and the entire visible range and part of the near-infrared region of the electromagnetic spectrum. The spectrometer connects via USB to your Windows or Mac computer. It comes with an AC adapter. You will need version 2.3 or newer of the free spectrometry app to use with the UV-Vis spectrometer. Download the latest version of the software from PASCO.com. The spectrometer comes with 10 disposable semi-micro cuvettes usable down to 220 nanometers. The cuvettes come with lids and a cuvette holder. These cuvettes are made of plastic. If you need high chemical resistance or need to investigate solutions at wavelengths below 220 nanometers, you can order the optional quartz cuvettes that are sold separately. Another optional accessory is the fiber optics cable, which you can use to investigate the wavelengths of light emitted from sources such as gas spectrum tubes. The spectrometer's light source is located here, below the white light graphic, and the light detector is located on the side with the colorful visible light graphic. Cuvettes are placed here. Fill cuvettes about 3/4 full. The included cuvettes have frosted and clear sides. Handle the cuvette by the frosted sides to keep the clear sides clean and free of fingerprints. Wipe cuvettes with a lint-free lens wipe as needed. Position the cuvette so light travels through the clear sides and reaches the detector. To investigate solutions, start by calibrating the spectrometer with your blank or the substance you use as a solvent. I used distilled water for the solutions I'm using today, so that's what's in this cuvette. In the software, click Calibrate Dark, and then Calibrate Light. And now you're ready to analyze solutions. This is a solution of red food coloring. Since I can see red color in the solution, I would expect a high absorbance of green light in the visible spectrum, since green is a complementary color to red. Let's start recording data to test this expectation. I'm going to scale my data, and I'm going to increase the number of scans to average to improve the display. There we go. And as you can see, green wavelengths are highly absorbed by the solution, but red is not, allowing mostly red and other wavelengths to be transmitted through the solution to our eyes. You can also see that the spectrometer detects some light absorbed by the solution here in the UV region. Our eyes can't see this. So the UV region appears here because this molecule in the red food coloring contains a highly conjugated organic molecule with many adjacent double bonds. So what does the absorbance spectrum of a clear organic compound look like? Here's an example. This looks like water, but it's actually ascorbic acid, which is otherwise known as vitamin C. This ascorbic acid solution is clear. Now let's look at the spectrum. I'm going to scale the data, and you'll notice that this solution does not absorb light in the visible region, but it does in the UV region. Now I can use the coordinate tool to identify the peak absorbance. And you'll want to keep your maximum absorbance below 1. I've just shown you one way to look at solutions, but you can complete a Beer's law analysis to determine the unknown concentration of a solution if you keep your selected peak, stop collecting data, and move to the concentration tab. Or you can investigate factors that affect the rate of reaction, such as redox or hydrolysis reactions, when you move to the time tab. And if you go to the Analyze Light tab, you can use the optional fiber optics cable to identify an element in a gas discharge tube or explore atomic energy level transitions. To properly position the fiber optic cable, find the triangle on the cuvette housing and line it up with the notch on the cuvette holder on the spectrometer. Position the other end of the cable near your light source, but not touching. Turn on your light source, start collecting data. Let me adjust the distance and position. And I can improve the signal if I auto-set the integration time to eliminate background noise. The software does this automatically. There we go. And now I can run through the reference lines for known elements. Here's hydrogen, which does not match my data. The next one is helium. Does not match, and argon does not match, neither does xenon, but mercury does match. So these reference lines help you identify an unknown element from a gas discharge tube. Visit the UV-Vis spectrometer product page on PASCO.com for more information about the spectrometer, the fiber optic cable accessory, or the quartz cuvette accessory. And check out PASCO's experiment library for investigations you could complete with the UV-Vis spectrometer, like the analysis of aspirin tablets. Thanks for watching, and see you next time.